I'm Keith. I'm at Cornell now, for those of you who've never met me. I just moved there in April, and before then I spent 6 years before at the NSA. About today are some experiments that we've done at very low temperatures with nanomechanical systems. They're much less practical-minded than what Arun has just told you about. But we're trying to uncover some of the basic quantum properties of matter. That's one way to say it. And I hope you'll see that in the upcoming slides. Just that I wanted to give the organization this talk to tell you where we're headed first, or where we're headed ultimately. And then I'll tell you where we've been and how we're trying to get there. The experiment that we'd like to get to, and what we're setting up now at Cornell, is something along this lines. So imagine you had a small mechanical system, some sort of cantilever, and imagine you coupled it to some real quantum mechanical two-level system. This thing's blinking. There we go. Imagine you coupled it to some real quantum two-level system. Think about a spin. I'm thinking about Cooper pair box qubits, so qubits are good. But let's just imagine a two-level system. And that the mechanics responds to the state of the two-level system. So simply put, that just means that, let's say the mechanics moves to the left if your spin is up, and it moves, and you form this kind of state. So this could be a quantum mechanical way to describe this state. My mechanics is moved to the left, and my spin is up. And if I put the spin in the down state, then through this force, I can produce this system state. So the spin is down and the mechanics is to the right. And the real question with this kind of interaction, so all that seems trivial at first. Hang on, wait. The thing that's interesting is that what happens if you can produce a superposition of this spin state? So which way will the mechanics move? Okay, it's a very naive question. If you actually believe the universe is quantum mechanical, then you should expect the mechanics to have to go both ways. So you should be able to produce what's called an entangled state, where the spin is both up and down, and the mechanics is both left and right. So that's a really odd situation. And when I look through an optical microscope and look at a mechanical system that we've made, I never see them two ways. I see them this way or that way. So there's a lot to this story about engineering this system. Can you get, for instance, decoherence times of your mechanical system long enough so that you could actually produce this kind of state, and long enough that you actually then make a measurement? So that's a longer story. We've published all the details of these kinds of estimates in a PRL a few years ago now. And what's very surprising is that if you actually make estimates of decoherence times in mechanical systems with the Qs that we have, that they actually should be in microseconds or more. And it's surprising that that's possible. So this is where we're headed. This is what we're trying to do, and this is the experiments that we're setting up now at Cornell. Yeah.
So it's going to be stupid, but I don't understand how you can do this, because in order for the cantilever to determine the Hamiltonian, it has to have some energy associated with its displacement. And if you have energy associated with displacement and it has some mass, it has a restoring force. So the only way this works is if dissipation then is turned on, which means then none of these are eigenstates anymore. That is, if I take a mass spring system and I drive it, it starts to ring.
Yeah.
It doesn't just move and displace,
yeah,
because that has, in order for it to do that, it had to throw away thermally some energy.
That's right.
So what am I missing here?
Well, you're right. You can imagine this. You're right. You have to have. You don't want dissipation. Dissipation actually increases your decreases your decoherence time, and that's pretty much the only story there is for decoherence in mechanics is the dissipation. But you can imagine this experiment done dynamically, where I suddenly produce a superposition, and then one half of the wave function for the mechanics starts heading off, and it's going to be dynamical. And actually, the dynamics is essential for the measurement, because you're going to produce an entangled state.
I'm okay with the dynamic.
Yeah, it's going to be a dynamical effect. Yeah. So it's going to be entangled, then unentangled, then entangled, then unentangled. So anyway, this is the kind of totally, sort of out there kind of thing that looks possible, and something we'd like to try to demonstrate and make. And with that, I'll go on now to where we've been and how we're trying to get to these kinds of experiments. So, where we've been, this is an experiment where it's very much in line with the kind of theme of this conference workshop, where this is an experiment that I did as a postdoc in Mike Ruckus's group, where we looked at thermal transport through an engineered nanostructure down at very low temperatures, below a Kelvin, down to about 80 millikelvin. And in this limit, it's similar to kinds of things that Arun was talking about. In this kind of sample, the little bridges here of silicon nitride coated with niobium, the little bridges are actually small compared to the wavelength of the sound that you're using. And they act as one-dimensional channels for the phonons. And they're short enough that they are ballistic. So in that limit, 1D ballistic transport, it turns out that phonon thermal transport is quantized. And it's given by this universal value here. So there's no speed of sound, there's a cancellation in the density of states, all that. And what's even more interesting is that this quantized thermal transport is not just true for phonons, it should be true for electrons, for particles of any type. And it's just recently been shown by Jukka Pekkala's group that you can see this quantized thermal transport between two resistors communicating through photons, through their Johnson noise. So it's predicted to be a very universal quantum transport, and it's in the same kind of universality or fundamental nature that, let's say, quantized electrical transport through point contacts or molecules that you see. But this is the energy transport quantum. So anyway, this is what you see when you go to small length scales. This is 100 nanometer kind of widths here, and ballistic transport. We see it at low temperatures. We saw it there. You can imagine seeing it in much higher temperatures if you made the size length scales much smaller. So this is one place where we started. From my point of view, as someone interested in the quantum properties of mechanical systems, the heat flow through these bridges is through phonons, through mechanical vibrations. And some people say that this experiment was one of the first manifestations of a quantum mechanical effect in a mechanical nanostructure. So you can see quantized thermal transport in devices like this. Okay, so what we moved on to after that, this is when I went to work with NSA and had a lab at the University of Maryland, was to start to build nanomechanical devices where we're coupling single electron transistors to these devices. And the estimates, the numbers actually showed that this kind of device should approach the uncertainty principle in position detection. Now, if you're into this kind of physics, there's many proposals of things that should work near the uncertainty principle. And what was ultimately the punchline, what was really surprising about this, was that it worked the closest to the uncertainty principle that any position measurement has ever operated. We're about a factor of 5 away from uncertainty, Heisenberg uncertainty, and it's actually closer than when any gravitational wave detector, including the current LIGO, is as far as approach to the Heisenberg uncertainty principle limit. The other thing that I'll show you is that we can make these mechanical systems cold, that they're getting close to their quantum ground state. And I'll show you how well we've done with that. But let me just talk about the structure. The junctions for the SET are at the corners here. This is an aluminum line. The nanomechanical bridge, it's like 10 microns long here, 8 in this case, I think, and it's coated with gold. And we apply a big voltage to this nanomechanical resonator, and when it moves, it changes the charge at the SET and changes the transport. So that's the coupling mechanism. If you zoom out, in this particular device, we used a silicon nitride membrane, and we etched some holes into the membrane and left a suspended wire. And here are the SETs, the gray and the aluminum there. If you zoom out even further, you can see some of the details of a microwave matching network. So we launch microwaves at this device, and this LC network transforms the impedance of the SET, which is 50 kiloohms, 100 kiloohms, transforms it down near 50 ohms, and what reflects back tells you about the resistive impedance of the SET. So we do microwave reflectometry in order to read out the SET. This is called the RF set technique, and it was first demonstrated by Rob Schulkoff at Yale. One thing that's fun is that you can, at low temperatures, you can make these near-perfect coils. This is out of aluminum, and so once it's below a Kelvin or so, you can get this nice superconductivity in just a perfect coil. So anyway, that's more or less what the samples look like. We've moved on away from the membranes, and we're etching surface micromachining the resonators now. So if you put all that together, what you can look at is the noise power, just the noise coming from the SET at the mechanical frequency. This one's around 20 megahertz. And you can actually see the thermal vibrations. This blue one, the one to the right here, corresponds to 100 millikelvin, and that's about 100 mechanical quanta in the beam. And you can use the peak height, the thermal noise, relative to the baseline noise as a measurement of the sensitivity. And what you can show is that our noise temperature of our detection system, which is given by this baseline, is only 33 times away from the uncertainty principle limit for a noise, quantum limit for the noise temperature of an amplifier. And if you square root that, in this particular case, it's about a factor of 5.8 from uncertainty.
Question.
Yeah,
what is quantum TQ? How do you define TQ?
It's there's I forget the formula. It's basically h bar omega divided by k Boltzmann, and then there's a log 3 underneath there, and that's the quantum limit for a linear amplifier. So amplifiers have a quantum limit. Simple harmonic oscillators have quantum limits, and when you do the detection, you see a half h bar omega from each piece. For more practical purposes, what may interest some of you is the kind of force noise sensitivity that we have. And if you can't read this, it's 10 to the minus 18 newtons per root hertz right here at this peak. And this is the same level of force sensitivity that Dan Rugar has on his single spin detection, but this is up at nearly 10,000 times higher frequency. So using these kinds of high frequency mechanical systems with very good position detectors might be useful for a variety of force detection kind of applications. So the areas of these peaks here is a measurement of the expectation of x squared, right? It's the RMS position fluctuations, and that's simply related to the temperature. Okay, so if I take the area of these peaks versus the temperature of the refrigerator, I can see that the mechanical mode actually thermalizes with the dilution refrigerator, and the lowest point that we see corresponds to 25 millikelvin, which is about 25 quanta in this small mechanical beam. So this is the closest to the the closest to the ground state that any mechanical system has been observed. And we think we can push this down to the ground state by using some other kinds of cooling techniques. It's a longer story, but it's something that we're trying now, using electrical resonators coupled and pumping it in the right way and actually actively cooling it. So anyway, this shows us that the mechanical mode indeed gets cold, and the points here are the areas of those, the area of the peak in the noise spectrum. So in our paper in 2004, we showed that we could get very close to uncertainty principle. This black line here is from the readout of the electron current through the SET. This is the shot noise limit of reading out an SET. So we can't quite get to the shot noise limit. The red line here is the back action of the SET onto the mechanical device. So if I couple the SET and the mechanics too strongly, eventually the back action, the actual push backs from the SET, and I'll talk about that in a second, start to decrease your sensitivity. So there's a sweet spot. And this curve actually what motivated me to try this experiment, because the SETs come very close to the uncertainty principle in principle. Okay. So this is how far we got in 2004. And what we wanted to do was, in our next experiment, was to actually go to this limit and to try to see if we can actually see the back action from the SET and quantify it and say how good is an SET as an amplifier. Does it itself approach the uncertainty principle? So the back action in these kind of mechanical or SET mechanical systems works like this. Let's first talk about an interferometer, and you'll see that there are many of the same kinds of pieces. So imagine that I had an interferometer, and I set it up with a fixed mirror and then a mask that can move. And I shine light at some beam splitter, and some of the light goes off of the fixed mirror into my detector, and some of the light goes off the flexible mirror into my detector. Now if I held this movable mirror fixed, if I just made all the mirrors fixed, I'll still have noise on my detection, because the photons are quantized. I'll have shot noise of the photons. Okay. If I allow this mirror to move, the mirror should actually recoil when the light bounces off it. So there's a static pressure pushing on the mirror from the light. It's called ponder motive force. And there's also a random component to that due to the fact that the photons impact randomly. Right? It's this rain of photons hitting it. So this mirror should be vibrating or moving around randomly due to the stochastic noise forces from the photons. That should make the mirror move. That should be imprinted on the interferometer signal that goes to your photodetector. And when you consider experiments like LIGO and things like this, these are the kind of noise terms that go into the optimization. In an SET, what you have is you have a mechanical structure. You have the SET. You have electrons running through the SET into some amplifier. So even if there were no mechanical structure, I still would have noise in my detection of my electrons because the electrons are quantized. They come in discrete particles, which is really similar to the shot noise quantization of the photons. When the electrons jump on and off the island, the potential of the island here will rise by about 100 microvolts. That's engineered. That's what makes the SET work. But there's what it means is that there's a kind of telegraph noise signal here at the SET. That voltage noise is going to make force noise on the mechanics. That force noise will make it move, and that'll imprint onto the current running through the SET that I detect. So you can see that there's the back action from the fluctuations of the SET island is going to drive this mechanical system. And one thing you might want to think about it in sort of a general way is that, measurement, quantum measurement, how does it happen? I have some object, and I shine some particles on this object, and I look at where they scatter. And where they scatter tells me about the position of this object. And ultimately, there'll be a pressure from that shining those particles on there. That's a static force. But there's also the random component because I'm not controlling exactly when these particles come out. So this is the similar kind of system where I'm basically running electrons through this object, and they're scattering through a Coulomb interaction off the mechanical beam. And that's essentially the back action mechanism. So, that's what we wanted to see. The theory for all of this was really well established a couple years before we got to the measurements. And I just wanted to mention that Ivar Martin and Dima Mazorski were ahead of the curve of all this. And what they looked at was a mesoscopic device where they had a tunnel junction coupled to a mechanical mode. This was a theoretical study. And they showed that the tunnel junction would act as a thermal bath with a temperature just given by the drain source bias. And they went on also with Andrew Armour and Miles Blanco to show that if I had two tunnel junctions in series and made an SET, that the SET would act as a thermal bath with a temperature just given by drain source over 4. Isn't that neat? I mean, that you get the mesoscopic detectors, all the kind of transport that's going on, that you can get this simple rules of thumb about how the detector, what temperature it will act as far as its back action onto a mechanical system. So it's these very simple rules of thumb just with drain source biases. So let me just kind of jump ahead a little bit. As the theorists got more into what actual experiments we were doing, the theory got more sophisticated, and they could handle a superconducting SET. And a superconducting SET, there will be points of resonant transport. The Josephson quasiparticle resonance, the double Josephson quasiparticle resonance. There are points where two levels line up and you can have the Josephson effect, moving the electrons. But if you have this resonant point of transport, this is the temperature that you get for the superconducting SET. Gamma is the lifetime, it's a line width of the resonant transport process. Delta E is the detuning of your voltage. So are you right on the peak? Delta E would be 0. Then you can red detune or blue detune. Okay, you can either add energy or subtract it. And what's really interesting is that the SET temperature can be both positive and negative depending on your detuning. What's really nice about this formula is that it's also exactly the same formula you get for Doppler cooling or also for cavity cooling. So it's a very generic kind of formula that you get when you have some sort of resonance with a line width, and then you can control the detuning. Okay. So I won't dwell on this too much, but I just wanted to tell you that the transport through SETs in superconducting state can be complex. These lines that come out here are the Josephson quasiparticle resonances, which is the alignment of one level, an electron level with one of the leads. And down here, this peak that shows up, this is a map. The colors tell you current This is the drain source on the SET. This is a gate voltage, which is changing the alignment of the levels. You can get a point where you have resonance that happens with both leads, left and right, and that's the double Josephson quasi-particle peak here. What's interesting was that the theorists told us that on this map there would be places where the SET would act as a cold bath and could cool our mechanics, and just by changing the bias by a few tenths of millivolts, that you could go to a hot place where the SET would actually heat it and cause like a lasing kind of effect. So this is what the theorists produced. I know it's hard to read, but as you go through, cross one of these lines, if you change your drain source, as you cross one of the lines, you go from a positive temperature bath, which acts like a damper, to a negative temperature bath, which acts like an exciter. And the double Josephson has a much more complex kind of terrain. So we biased ourselves for some of our measurements, our cooling measurements, right here, where we're supposed to get a nice cooling effect. So we biased there. And the first thing that you can see is that the damping rate of the resonator goes up as I increase the bias. And that's the SET pulling energy out of the mechanical system. So there's in regard to the topic of this conference, there's an example of energy transport between a single nanomechanical mode and the detector you're using to measure it. Okay? So it's the manifestation is that the Q of the resonator drops, and it's dropped by order magnitude. So the theory for this, yeah.
What's the time scale over which, if you're actually doing this experiment and you're looking at this, the SET, extracting mechanical energy out of that resonator?
So it's you bias everything up, and then you just go and look at the noise, and the Q is low. You're like, oh, the Q is low.
Okay.
So if you set things up and somehow can measure the mechanical displacements, and then put your bias where it was, acting as a damper, you'd see it relax with thermal relaxation time, which is just the Q damping rate. But this experiment was tricky because the object that was doing the cooling was also doing the position detection. So if we moved away from points of bias, our position detection goes away. Mm-hmm. So we didn't have separation between those two things. So it really limited what we could do. The sore spot in our measurements was that the damping from the SET should be the blue curve here, but we measured this red curve, and there's a factor of 14 difference between the SET damping and what the theory predicted, and that's something we still don't quite have a handle on. But given all the transport properties that can go on in an SET, I've told you about two of the possible mechanisms. There's a lot of stuff can go on there, so maybe all that complexity gives you extra damping. Okay, so the real punchline to this story, and this appeared in September, was this curve here. This is the temperature of the mechanical mode versus the temperature of the bath. And what you can see is that the brown points here, the 1 volt is where we have very weak coupling, and it shows a straight line. It's hard to see. And that's just noise thermometry. So the nanomechanical mode is just following the bath temperature if you're at very low coupling. And then as you increase the coupling strength to the SET, eventually you get the black curve, which is heading towards flat. And the SET is supposed to act as a temperature bath of 200 millikelvin. That's what the theorists told us. And we see two pieces of evidence for that. If we go to low enough temperatures, the mechanical mode here saturates at a temperature equivalent to somewhere near 200. The other evidence for it is that if I have the bath and the SET both at 200, the mechanical mode should then be at 200 as well. And that's why all the curves cross somewhere near 200 millik. Okay? So this crossing point is another indication that the SET is a temperature of around 200. The other interesting thing to come out of this was that, and this was staring us in the face for a long time before we realized that this simple statement, is that the SET is cooling the mechanical mode. It's actually pulling down the temperature. So as I increase the bias, I can decrease the fluctuations in the mechanical mode. So it's actually just getting pulled, the mechanical mode is getting pulled towards the SET temperature due to the high damping. So it actually can cool it.
How is SET temperature related to the actual temperature of the system?
Yeah, they're not that related in the end.
If I increase the total temperature, so
yeah,
to room, will it require eventually?
To room, everything goes in our experiments stop at probably about 800 millikelvin.
I know.
But
if I increase it.
So as you increase the temperature of the SET, the electron gas temperature increases, right? But the temperature that I'm talking about is a back action temperature which is all about how much it can damp and what kind of force fluctuations it gives. And that more or less remains fixed, because that's just about the transport through the device. So you can decouple the electron temperature, the actual physical temperature, from the noise temperature of the thing.
So you're making a point about 200 millikelvin where all the points cross,
Yeah.
which is actually the temperature which is consistent with the minimum temperature you can get because of the resistance
Yeah.
formula. So is there a way to change this temperature?
Yes, there is. And it's the temperature of the SET is given by the resistance of, it's given by the line width. Ultimately, the minimum temperature of the SET is given by this gamma, and that's the resistance. So, you can imagine an experiment where you could go to a very high resistance tunnel junction and then have a much colder SET. But that would now require two devices on each side of the mechanics. One is a position detector, one as a cooler. Because right now we have a SET that's optimized for position detection, so we can actually see these noise fluctuations. If we went to a high resistance SET, we no longer would have the position sensitivity we want. So it becomes a more complex experiment.
So basically you didn't do it.
Oh, no. No, we didn't do it. This ended up taking us about 2 years to sort out. And the experiment with the data that I showed you is about 6 months worth of data. So it's a pretty big effort to try to go there. I don't know if we'll ever do it. I think we're going to move on to all these qubit experiments. But it sure would be fun for someone to do it. And maybe someone will see it in some other context. Life's too short. Fridges are you don't have enough of them. You don't have enough students. All that stuff. But there are lots of neat experiments to try. So if you go to the last thing I wanted to say about this is that if you go to the double Josephson quasi-particle peak here, where the back action effects are actually stronger, whether you're below or above the resonance, you can actually drive the system and make the line widths narrow. So this is an example of going from the SET acting as a damper and a cooler and acting as a negative temperature bath and a negative damper. And the theorists like this, my friends Osh Clark and Miles Blanco and Andrew Armour, have written a couple papers where they compare this kind of physics to a laser process. And in fact, for certain limits, it can act like a micro laser, where the actual noise properties of this mechanical mode can be below some quantum limits. It becomes number squeezed. Anyway, so there's some neat physics there. And it's like a lasing process. The point to remember is that if you bias yourself at the right place, you can end up with a self-sustaining oscillation that's like the SET is pumping energy into the mechanics, and it's driving it and self-sustaining it. Okay, so all of that is about how a mesoscopic detector couples to a single mechanical mode and can exchange energy with that. Either you can tell where the mode is, where the position of this thing is. You can the back action of the detector can cool, it can heat, all that business. Another project that we're working on with in collaboration with Anton Zeilinger's group is to try to couple small mechanical devices to quantum optical fields. And what we had the idea was that we could try to make flexural structures. These are little bridges, little mirrors here, that are made from dielectric super mirror material. So take the mirror material that Jeff Kimball and the cavity QED people use, where you get 1 part per million loss on the material, on the reflection, and to see if we can undercut it and make something flexible. And then to use it for their experiments. Send it off to Vienna for those experiments. So that's something where I have one student who's heavily involved in this, and these are the kind of chips that we send with lots of micromirrors. They're very, very large. They're hundreds of microns long and maybe 50 microns wide in order to get the spot size of the laser onto this thing and also have high Q for the cavity. So these are some blow-ups of the mirrors. We make little trampolines or little bridges, things like that. And the experiment that we're actually going for was proposed by Paolo Tombesi, and it's to entangle the optical field with mechanical motion. There was 3 papers in Nature, all piled up at once in December, and it was all about optical cooling of small mechanical things. And it basically was stimulated by a conference in Dresden last spring, where the group that I work with Zeilinger and Aspelmeyer, showed some data of this kind of cooling effect from optical fields, and then suddenly the other guys who were working in this direction all pushed their papers as well. So there's like this pileup of papers of cooling. And the basis of our technique was very simple. It was an optical cavity, so our mechanical mirror here, it's flexible, some sort of cavity, and you arrange things such that if the cavity changes its length, you're going to change the light pressure inside the cavity. And the delay time can produce actually like a frictional force. Okay, so there's the back action in this case is due to the actual energy in the cavity due to the photons. It's the ponderomotive pressure. And the friction, the damping that you get that's going to allow you to cool is given by the time delay of the relaxation of the energy with the motion of the cavity. So we made for them what looks like the world's crappiest device, but somehow it gives some reasonable results. It's a Q of 20,000 mechanical mode. It's this dielectric material, and then we use xenon difluoride to etch underneath it. And here's some examples of what they saw in the cooling. This is the more or less the punchline here. This is the fluctuation spectra at 300 Kelvin, and then if you bias your laser right on the right side of the fringe, you can actually cool the mechanical mode down to 15 Kelvin. And people have done better cooling than this. This was the punchline for this experiment was that the cooling is done through ponderomotive pressure, through the fundamental pressure of the light, not some other force that you apply by using feedback from a good position detector. But this is actually the natural cooling you get in a cavity due to the pressure of the light. Vladimir Brzezinski calls it the optical tranquilizer. And this existed in the literature. You know, it's like classic Russian kind of situation where, yes, this existed in the literature for 30 years before this was done. So anyway, we're involved in this, and one of the mysteries in this experiment is why the mechanical cues are so bad. And we don't understand it, actually. Structures are a few hundred microns long, 5 microns thick, 20, 30, 40 microns wide. It's really big stuff, right? You'd expect, at 4 Kelvin, you'd expect cues of hundreds of thousands, maybe even a million in something if you made this out of silicon. And you can see the layered stacked material here, the dielectric stack. So we get very low cues. Typically, we get cues of 1,000, a couple thousand, and that 20,000 was anomalous. So we don't know where the cues are, or why we're getting such bad cues. We think it's all the ragged edges here. If you zoom in, you can see lots of, from the deep reactive ion etching, you can see lots of ragged edges. I'd be really curious if anyone has any ideas how to make very clean edges on this kind of thick material. It's silicon oxide, and then it's tantalum oxide, or titanium oxide. That's the two dielectric materials. So etching that is just miserable.
And do you see a shift in the cube when you undergo this ponderomotive cooling?
Yeah, this is something that I didn't realize when I was going into all this a couple years ago. But you must see, if you see cooling, you must see a lower Q, because I have the room temperature bath, I have my mechanical mode, and it's coupled through dissipation. And then if I'm going to cool it, I've got to cool it to a lower temperature bath through even higher dissipation. So the Q has to drop if you're going to couple. And it's the same, just like with optical cooling. If I have an atom in a cavity, its coupling to the environment is very weak, so its Q to the environment is very high. And for me to laser cool it, I have to lower the Q. Right? So this is a very generic kind of situation. Okay, so...
I'm sorry, why do you think that the roughness causes the low Q at that? I didn't get it.
We don't know. We're desperate.
It's
everything else is really
okay.
clean. Everything looks good. The only thing I can see wrong with the sample is that it's rough on the edges. Okay. And I could show you some SEM pictures that are much more horrific than this.
It's not related to layered structure. Have you tried just a bulk piece that's rough on the edge?
No, I've seen examples where people have like silicon out of this kind of thing, and they see really hot.
SiO2 or some class.
Yeah. I guess I would have expected much higher Qs. Yeah.
What about your tantalum oxide, which is silicon dioxide? If you have sharp points that heated buffered oxide edge, short dip will smooth out.
We need something that's. I want something that's like. Yeah. So we're thinking about going in with an ion mill and trying that, but. Well, send me a note. Send me an email. I'd be happy to think about it and take any suggestions. We're up. Yeah. So the last thing I wanted to mention was, and this is just nuts and bolts engineering, is how do you get electrical signals and electrical power out of nanomechanical things? This is like, a classic problem. If you go to the physics labs, you go to Mike Ruckus's lab or something like that, you'll see everybody with 9 Tesla magnets. Like, great, okay, you can see the mechanical mode, but we're going to drag around a superconducting 9 Tesla magnet to do any real measurements with. So when I was going through all this back action, I started to understand what the real model between a gate, like maybe it goes to an SET, and a mechanical mode is. And I rediscovered the model that the MEMS community has known forever. And it turns out, if you go through the engineering of that once you know that model, you can actually do capacitive detection of nanomechanical modes. And this is how I did it. So the mantra, if you read nanomechanics literature, they'll tell you this cannot be detected capacitively, efficiently, because this is about 10 attofarads, 30 attofarads, and even at radio frequency, this is a gigohm impedance. So it's hopeless, right? Well, it's just wrong. That's true if you don't have a DC bias. As soon as you apply a DC bias to your gate, the model is no longer just a capacitor between the two, but a parallel RLC. And forgive me for the people who know this stuff already. This is totally obvious, but it was unknown to the MEMS guys, thinking that this would be impossible to accomplish. So you go through the model, and you find out that on resonance, RM. So on resonance, L and C cancel, and you're left looking directly into RM. RM turns out to be a megohm, maybe down to 10 kiloohms. So that's not so bad. And when you're off resonance, this channel is closed, and you're looking through this gate capacitor, and it's about a gigohm. So there's this enormous contrast in impedance when you go off resonance and onto resonance. And this kind of resistive impedance is well within the range of LC impedance transformation, so that's what we did. So you start with this impedance model, just a voltage bias nanomechanical system, and then you take a chip capacitor, sorry, a chip inductor, and then maybe a chip capacitor, maybe some stray capacitance. Depends on the model, depends on what your needs are, but it's picofarads, tenths of picofarads, something like that. And then I set up a reflectometry circuit, so you launch some power into this, and you look what bounces off. So if I've done this LC right, then it transforms down RM to 50 ohms. So I should get nice absorption when I hit mechanical resonance. And when I'm off resonance, this looks like an open circuit, and this will look like turn it into a short, and I should get a high reflectance. So basically, the reflectometry should change dramatically when I go on and off resonance. It's a mechanical system. And I use just some bias T to bias up the gate of the mechanics.
And you sweep the inductance then? Because you don't know necessarily...
Yeah, but so it turns out that, so in practice, we could sweep the inductance with a magnetic field if we wanted. My students who have experiments where they can't do that just do a bunch of dippings and get an adjustable capacitor right. So the Qs that, LC circuits, the best Q you can get in an inductor might be 50 or something. So it's not that hard to tune it. And after a couple dips into low temperatures, we do all our experiments at low temperatures, so we want to see these networks work at low temperatures. After a couple dips, you can get it just right. So everything's reproducible enough that you can get a resonance frequency at room temperature and compare it to low temperature. Anyway, it's details, but you can tune it. So this is it working. This is the reflected power versus frequency. Here's a high Q nanomechanical mode. The width here is from the finite width of the LC tank circuit, and if you make the tank circuit degenerate with the mechanical mode, you can actually see an enormous, big change in reflectivity. And this is zooming in there. Here's the LC tank network, matching network, and then here's the nanomechanical mode. If you zoom in, you can see the high Q mode. So it's a nice technique. We're using it for fundamental experiments where we're looking at qubits, where we can't use magnetomotive, it would destroy superconductivity, all that. But it has a lot of really nice things. If you're working at room temperature in vacuum, it's particularly good. It's very low power dissipation, which might have advantages over a piezo resistive or things like that. And the other cool thing is that you can use it to read out arrays. And this might be the most important aspect to it, is that the impedance model is such that when one of these mechanical modes is not on resonance, it looks like an open circuit. It's 1,000 times higher impedance than when you're on resonance. So you can put a bunch of these devices all in parallel, and as long as they're resonating at different frequencies, they won't load each other. Okay? Because they all look like more or less open circuits, and then the whole circuit drops down when the impedance drops when one goes on resonance. And so that's what's shown here. Here's a forest of a bunch of different modes. This one is where actually two of them lined up. There's actually two curves here. It's not easy to see, but what we've done is turn on one set of resonators and then turn on the other. and so you can switch which ones you want to see. The capacitors, the LC network, is such that you could have separate chips with separate processing. Let's say they're coated with various kinds of chemically sensitive, one might be different than another. You could easily have different chips that are lined up, all read out on one RF circuit. So for the parameters that I'm working with at tens of megahertz, you can imagine, you know, a bunch of different dies all read out on one high frequency line, frequency multiplex like this. So it might be useful for sensor, people doing sensors. Last thing I wanted to say, so this will be really short, is this is unrelated to the nanomechanics, sort of, but it may be related. People in this community might be interested. Camila Kenzie at BU and I have been working on a high-frequency STM, and it's just recently started to work. You can take an impedance matching circuit to a high impedance tip of an STM, and do this reflectometry technique. And we've shown STM now with bandwidth in the megahertz. It has the same sensitivity as normal STM. The bandwidth is increased now in megahertz. Some of the neat things you can do with it is, you can imagine if you were looking for ESR signals, you know, that would be a nice thing to kind of to go after. We've been looking at noise on surfaces, and you can do, using shot noise and voltage noise, you can do thermometry on a surface with atomic resolution. Okay? So just by looking at noise, you can tell temperature. We put it over a nanomechanical mode. You can see these high-frequency modes vibrate underneath it. So we have this trampoline, a silicon nitride trampoline, and we can, just by parking the STM, we can see all the radio frequency modes of this thing. The other thing that's neat about it is that the impedance matching and all this is transparent at DC. So you can do your normal STM at low frequencies if you want, but then you have this high-frequency network if you want to use it too. So this is we think it's a significant improvement to STM, and it opens up the bandwidth of STM by a couple orders of magnitude. I'm just going to stop there. This is my group that I work with, lots of collaborators, a bunch of students, a couple are still at LPS. I have a group now starting at Cornell. I have 3 or 4 students there, and then my collaborators. My parting with NSA was not a pleasant experience, and I just want to put that out there in the community that I would not recommend working there as a ambitious scientist. Let me just put it that way. Anyone who wants to know what it's like to work at NSA as a scientist, I consider myself lucky to have achieved this stuff in that environment, and lucky to have escaped. So, and I know we laugh about it, but it was not a pleasant experience. This is the slides, the summary slide, where I've just here's the basic numbers. Some of the things that you might be interested in are force sensitivity and position sensitivity, especially.
Okay. Well, let's thank Keith, and let's congratulate him. Actually, we're now at the break time, so I guess I'm trying to keep on schedule. Maybe we could break unless someone has a really short question. If not, I know Keith has to run to the airport right away, so if you have a question for him, talk to him quickly. I think in order to stay on schedule, we're going to try to have a shorter break than normal. So if we can kind of get back here at 10:15.